So this one from, like I said, May-June 2023, paper 2-2. So the first part is a progressive wave travels through a medium. The wave causes a particle of the medium to vibrate along the line P. The energy of the wave propagates along the line Q. Compare the direction of line P and Q if the wave is transverse. So transfer is defined as if the wave direction of the energy transfer and the direction of the vibrational particle is perpendicular. So in this case, the direction of line P and the direction of line Q is perpendicular to each other. Okay, but just the keyword is perpendicular. Even if you write the word perpendicular, you'll be getting marked for this one. Likewise, for longitudinal wave, they have to be parallel. So the direction of the energy transfer and the direction of oscillation of particles, they are in the same line for longitudinal wave. For example, sound wave, and transfer wave, for example, water wave. Okay, so let's take a look at the next one. Now this question is specifically from the topic harmonics that we have been studying over the past few lessons. A tube is closed at one end, as you can see over here. A loudspeaker is placed near the other end of the tube. So we have a source of sound on the left side of the tube. So left side is open and the other end is closed. Now the first question is, can you tell me which case is that? Case number 1, case number 2, or case number 3? And if you want me to scroll up, I can show that to you also. So do you think this one is this case? Stationary wave produced between one open end and the other closed end. The only difference is in the question, the right side is closed and the left side is open. So if I scroll back once again, here we have this thing. And at this point we have an antinode, at this point we have an antinode, and at the closed end we must be having a node. At closed end we always have a node. So if I try to complete the diagram, between antinode and node there must be between two consecutive antinodes there would be a node in the middle. So the first antinode is over here. All right, so let's get back to the question. So at the start we have an antinode and the next antinode is somewhere over here, and we know that between two antinodes we must be having a node, and the right side of the tube, since it's a closed end, so there must be a node. Now before doing anything, I haven't read the questions yet, but what I'm going to do is I'm going to draw a stationary wave in the tube. So the wave would look something like this. So I'll start off with the antinode. So antinode means something like this, and at the node I have to decrease the amplitude all the way to 0, and this is the next antinode, something like this, if you be more precise, and then node over here. And then if the wave is moving fast enough, it will look something like this. Okay, it will look something like this. And my first question is, if we scroll all the way up to the third category, for which the wave is produced between one closed end and the other one open end, can you tell me what harmonic is this? First harmonic, second harmonic, third harmonic? Just by looking at the shape of the wave. Second harmonic, exactly. So this is what we have drawn over there. Exactly, that's the second harmonic. So just take a look at the formula for the wavelength for the second harmonic, as well as for the frequency for the second harmonic. They might ask us to find frequency or wavelength, okay, or the length of the tube. So we must be aware of it. If we have the second harmonic in this case, which is sometimes also called as third harmonic directly, but then the third one should be called fifth. But the way we are doing it, we just simply call it second harmonic or the first overtone. So the wavelength in that case equals to 4L over 3, and frequency equals to 3V over 4L. So I'll just write down these formula just in case. We don't know if they'll ask us to use those. So wavelength equals to 4L over 3. Was that the case? 4L over 3. And frequency was 3V over 4L, right? Frequency was 3V over 4L. All right, so what do we need to do in the first one? In the first part, we have to find the wavelength of the sound. Okay, so this one is very easy. It has nothing to do with the length of the tube. We are provided with the frequency, we are provided with the speed of the wave. We can easily find the wavelength. V equals to f lambda. Doesn't get easier than that. Lambda equals to speed divided by frequency. Speed is 340 meter per second divided by frequency is 1.7 into 10 to the power 3. So if you hit it on the calculator as it is, you'll be getting 0.20. Alright, so this is what we get for the first part. The wavelength of the wave is 0.20 meters. Now what is the length of the tube? So once again, you have plenty of ways to solve this question. The simplest one, if you're good with memorizing the stuff, so you would be able to recall this formula, or you can also recall the general formula, and you then realize this is the second overtone, this is the second harmonic, and in this case lambda equals to 4L over 3. I'm going to write down the formula. Lambda equals to 4L over 3. Then I can rearrange it for length. Length equals to 3 times lambda divided by 4, and that would be 3 times lambda 0.20 divided by 4, and if you hit it on the calculator you get 0.15. So the length of the tube is 0.15. Or the other way is, you check out how many wavelengths are there in the tube. In order to answer that, you'll first have to draw the stationary wave like I've drawn with the red pen here. You first need to draw the stationary wave. Then I know this thing, that the distance between two consecutive antinodes from here to here, you get half of the wave. So this is lambda by 2. And then from consecutive antinode to the node, you get a quarter of the wavelength. Yes, like this. And then what we get is, if you just make the denominator same, you'll have to multiply this one by 2, denominator also by 2. Then you add the two fractions, you get 3 lambda by 4, and then you know in the total length of the tube you have 3 over 4 wavelengths. So you can say 3/4 of the wavelength, which is 75% of the wave. But in order to get to this one, you'll first have to draw the diagram for the stationary wave. So this is what I was saying. In the topic of harmonics, you must be aware of how to draw the diagrams, these things, and how to write the general expressions for 3 cases of the harmonics, the formulae. So the drawings, the diagrams, and the formulae, these are equally important. If you're very good with one of them, you would always be able to answer the question. So let's take a look at the next part. The maximum wavelength of the sound from the loudspeaker that can produce a stationary wave in the tube. Maximum wavelength. So for the maximum wavelength, can I say they are referring to minimum frequency? And minimum frequency, which is also called as fundamental frequency or first harmonic. So for the first harmonic, for the fundamental frequency, you get the maximum wavelength. So for that case, when one end is closed, the other end is open, what is the formula for wavelength for first harmonic? Let's scroll up all the way up. So this is the case. One end closed, the other end open. They are referring to maximum wavelength, means it has to have lowest frequency, which gives us or takes us to first harmonic. And in order to find wavelength for the first harmonic, we have this expression, lambda equals to 4L. So I'll scroll all the way down, and I know in order to have the maximum wavelength, I should be having the minimum frequency, which is the first harmonic. And for the first harmonic of this case, the wavelength equals to 4L. So lambda equals to 4 times the length of the tube was, how much was that? 0.15. 0.15 twice of 0.15 would be 0.3, and then 0.60. Over to the next one. Connected to this topic is a question of polarization, and apparently it doesn't seem to be a tricky one, rather easy one. For example, the first part, show that the intensity of the light transmitted by the first filter is 5.7 watt per meter square. Okay, seems very easy. So let's call this one I, and the previous one, let's call it I naught. This is the angle. Let's call this angle theta, as we call, but this one they can call alpha if they want. We'll go with theta. So the formula that we have is I equals to the new intensity equals the old intensity times cos square theta. So new intensity needs to be found out. The old intensity was 8.5 times cos squared, and the theta is 35. And when you hit it on the calculator, you have to be careful with it. You don't have to take the square of 35. You have to take cos 35 and then take square of it. So 8.5 times cos 35 and then square of that function. So we get 5.7035, and in 2SF we can write exactly the same that we were supposed to show. And keep in mind the command word show, that in this one you have to show each and every step. You need to write down the formula, then you need to show the values that you have inserted. Only then you have to calculate the final answer. Okay, after that we have a second filter which we call as analyzer, the second analyzer in this case. And for this one, it is placed at an angle in such a way that the intensity is now dropped from 5.7, previously was 5.7, it is now reduced to 5.2. So we don't have to find the new intensity, rather we need to find the angle at which the new intensity should be 5.2. Now for the second case, let's call this one I naught, just for the second case, because for the second case this is the original intensity. Let's call this one I, which is a new intensity. Angle needs to be found out, and the angle that we'll be finding would be the angle with respect to the first filter. So we were very careful when we were studying the theoretical part of this thing, that the second angle is always with respect to the first one. So the new angle that we'll be getting would be the angle with respect to the first one, and if we have to find the total angle, we have to add the previous angle 35 also. So in this case you need to find the angle alpha, and the angle alpha is from the starting point, from the vertical line. So the angle that we'll be getting, if we once again apply the same formula for the Mole's law, we'll be getting this angle, the new one. Let's call it, let's say, theta prime, theta dash theta prime. But we need to find alpha, which would be from starting point all the way till here. So without doing anything, let us write down the formula for it. I'm doing it over here. I equals to I naught times cos square theta. Now I given as 5.2, I naught original in this case is 5.7 times cos square theta, and let's find the value of theta directly. For this one, I'll just need to divide 5.2. Let's do it in fraction. 5.2 divided by 5.7. Okay, and then I'll have to take square root of it, square root of answer. And then in order to find the angle theta, I'll have to take cos inverse of the new answer. So I get 17.227975, something like that. So I'll be writing 17 degrees, not Celsius, 17 degrees. So like I said, this angle 17 degrees is with respect to the first one, because whenever you apply the Mole's law for the second filter, the angle in that case is with respect to the previous angle, with respect to the previous filter. But since we need to find the angle from the vertical axis, so we have to add the previous angle of 35. So 17 plus 35 should be 12 and 52 degrees. So are we clear with this one? All right, so here we have the next one, a vertical tube, as you can see, of length. Okay, that much. Explain how stationary wave is formed from the incident sound wave. So a very trademark question, very standard question. They ask it several times. So we write the similar answer. The only thing is we'll just try to mold the answer with respect to the given situation. For example, in this case, the tube is vertical, so we can explain in that case, and the wave is sound wave. So all of that. So what do we say? The incident sound wave travels upward. Incident sound wave travels upward, which is reflected in the tube. All right, now we have two waves. One is the incident, the other one is the reflected wave. These two waves have same frequency and everything else is same. For example, time period, wavelength, speed, time period. These two waves superpose and form a stationary waves. These two waves having same frequency, you can say wavelength and speed, superpose, form stationary wave. So that's for the first one. So like I said, that's a standard answer. They keep asking this question many times, so we write the same answer. Okay, up next we have the next one. Sketch the graph to show the variation of the amplitude of the stationary wave with height h above the bottom of the tube. Before I answer that question, let me draw the stationary wave for this case. Can you tell me what case is this? What case of stationary wave is this? Is that case number 2, where both the ends are open?
Yes, sir.
Okay, so for the second case, where both ends are open, and we know that at the top we have antinode, so it must be something like this at the top, and in the middle we have a node. So I'll try to sketch the diagram. It looks something like this, and if the wave is oscillating fast enough, it looks something like this. Let's try to make it, and the central part is the node. Now my follow-up question is, so you're aware of it, that this is a case where two ends are open. Can you tell me what harmonic is this? For that case, is it the first harmonic, second harmonic, or third harmonic? So if I draw it horizontally, it looks something like this. What harmonic is this for that case? Isn't it the first one? So that's the first harmonic. So just quickly take a look at the formula for the wavelength, which is just obtained from taking a good look at the diagram itself. And that was a formula for frequency, which is, once again, you use V equals to F lambda. You simply insert the value of wavelength in terms of L in the formula of frequency. So I know that this is the first harmonic. Okay, so I don't know if I'll have to use this information or not, but I've written it anyway, that this is a case for where two ends are open, and for that case this is the first harmonic. So the lowest frequency that can be produced in this case is the one that you can see right now, and for that one wavelength was equal to, what was that equal to? 2L. Wavelength equals to 2L, and thereby frequency equals to V over 2L. Is that the case? See, same formula. So let's take a look at the second part, which is to sketch the graph for the amplitude with respect to the height. So when the height is 0, where's our reference point? The reference point is exactly over here. Okay, so that's your reference point. With respect to this reference point, you have to answer, when the height is 0, it means you're standing at this line where amplitude is maximum. How much is that? We don't know. Could be anything, but what we know is it is going to be maximum. So let's say the maximum that we can have is, we'll just have to choose any value since we have to sketch the graph. So let's say this one here is maximum. Okay, at height 0, amplitude is maximum. What about the height 0.30 meters? Exactly at the midpoint. What is the amplitude at that height? Height 0.30 meters. What's the amplitude? Is it 0? Because we have a node here, and matter of fact, node is defined as a point where the amplitude is 0. So can I say the amplitude is 0 at a distance of 0.30? And 0.30 would be exactly in between these two. Okay, so at a height of 0.60 meters, I move all the way to here. What point do we have? Don't we have an antinode? And if we have an antinode, doesn't that mean that we're going to have the same maximum amplitude? So we would be having the maximum amplitude equal to the one that you have supposed previously. And what does the graph for height against displacement look like? It looks something like this. In that case, it will look something like this. If it is starting from maximum point, it looks something like this. So 0 at a distance of 0.30 meters, the amplitude was 0. So we connect these two and that's it. And we don't draw straight lines. The question that could be there in your mind is, what if we draw the graph with straight lines? What if we draw the graph with something that looks like this. The answer is the amplitude with respect to distance varies as a function of sine wave. Now you see all the graph, the distance with respect of displacement is the same one, which is sinusoidal. So it's not a straight line, it changes with a function of sine wave. Okay, so what about the next one? For a stationary wave state, the direction of oscillation of air particle at a height 0.10 meter above the bottom of the tube. Okay, so if we have a sound wave and the direction of motion of the incident wave is upward, and since it is a sound wave, so at any distance the particle has to be moving up and down. It has to be moving parallel to the direction of energy transfer, or direction of what do you call that, direction of propagation of wave. So it'll be moving, in this case, since the wave is moving upward, so the particle must be oscillating up and down. Only this way it could be parallel to the direction of wave. Okay, then we have the next one, the phase difference between the oscillations of a particle at a height 0.10 and a particle of height 0.20 meters above the bottom of the tube. Okay, so one particle, so this is a height 0.30 meters. In the middle of that we have the height 0.30 meters. So our particles are below that, both of them. So the first one could be, let's say, someplace over here. The second one could be someplace over here. So the rule is all the particles that are there in between two consecutive nodes, they always oscillate in phase. They always oscillate in phase. So the phase difference in that case would be 0. Now what does that mean? So if you have, for example, if you have a wave, stationary waves that look something like this, and let's say this one is node, the first one, this is node here, this is the second node, this is the third node, this is the fourth node, this is the fifth node. So if you have the particles between any two consecutive nodes, this one, phase difference is going to be 0. All the particles in these regions, the phase difference is going to be 0. So let's say 1, 2, 3, 4. 4 red particles. What's the phase difference between all 4 of them? Answer is 0. Likewise, what's the phase difference between these green particles? 1, 2, 3, 4. These 4 green particles. What's the phase difference between green particles? The answer is 0, because these particles are between two consecutive nodes. Likewise, what's the phase difference between these blue particles? Okay, what's the phase difference among these blue particles? The answer is 0, because these particles are also separated by, are also within two consecutive nodes. But the tricky part is, if they ask you to find the phase difference between, let's say, green and blue and red, let's say, if they ask you to find the phase difference between all of the green particles and all of the red particles, in that case the phase difference would be 180. Why is that? Because the stationary waves just oscillates up and down. If I be explaining in layman terms, you can say the string, if it is a string, it'll just be moving up and down. The wave won't be progressing, it won't be moving left to right, it'll just be moving up and down. So once the red particles are going downward, the green particles would be moving upward. So they have opposite motion, opposite direction of motion. Thereby the phase difference between them would be 0. Oh, sorry, 180. Now the tricky part is, the twist here is, if they ask you to find the phase difference between the red and blue particles, not green this time, between red particles and blue particles, if they ask you to find the phase difference between red and blue particles, in that case the phase difference would be once again 0. Why? Because as the red particles go downward, the blue particles would also go downward. They're already at the maximum upper point. The only possible motion for the blue ones and for the red one is downward. So they'll be moving downwards. Is there a general way that we can answer this question? What we say is, if the nodes are separated, if the particles are separated by odd number of nodes, the phase difference would be 180. And I scroll all the way up over here. Yeah, we haven't discussed it over there in theory, so you can note it down as a general rule of thumb. Where was that? Yeah, over here. So the general rule is, particles separated by odd number of nodes, they have phase difference 180, and particles separated by even number of nodes, the phase difference between them would be 0. And keep it in mind, 0 is also an even number. What does that mean? If there are two particles and they don't have any node between them, that also means they are separated by even number of nodes, because 0 itself is an even number. Even number is the number which can be divided by 2. 0 can be divided by 2 because two zeros are 0. So let us apply these general rules on this situation. So what I'm going to do is, I'm going to label a particle, one of the particle, let's say one of the particle is over here. Let's call it particle X, someplace over here. The other particle is someplace over here. Now, what is the phase difference between these two particles? Okay, excellent, 0. And the reason being? Exactly. And if I show you the nodes, here we have the first one, 1, 2, 3, 4. So 4 nodes between them. What does that mean? They are separated by even number of nodes. And if you forget about this thing, you just take a look at their direction of motion. The particle here has to go downward, and the particle on the other side is also supposed to go downward. And if they're going downward, it means they are in the same direction. Their direction of motion is just the same, so there won't be any phase difference. And for stationary wave, the only two possible values for phase difference are 0 degrees and 180 degrees. And 180 degrees can also be like multiples of 180 degrees. That is just the same thing as 180. And likewise 360 is also just the same thing as 0, because after 360 you just return to the same point, or any multiples of 360 would be considered 0. Okay, anyway, let's move on to the actual question that we have. The speed of the sound wave is 340 meter per second. Calculate the frequency of the sound. So frequency of the sound wave needs to be found out, and frequency equals to V divided by lambda. V equals to 340, and lambda in this case is this thing. You see, that's why I've written the formula in advance, because lambda equals to 2 times the length of the tube. And if you forget the formula, what you can do is you can take a look at the diagram and you can work out how many waves would be there in the given length. So you see, in this part of the wave, in this part of the tube, you're having only half of the wave. You see this thing, start from this thing, that's only half of the wave. You get full wave only if you return to the same point. So from there you would also realize the same thing. Lambda in the length of the tube, you have half of the wave, and thereby lambda equals to 2L. And matter of fact, in derivation of these formula we use the same concepts. So lambda equals to 2L, so 2 times of 0.60 would be 1.2. So lambda equals to 1.2 meters. Now I can simply insert the value of lambda, which is 1.2 meters. We have made it very easy for us. Then we hit it on the calculator. So 340 divided by 1.2, what we get is 283 into SF. We can write it as 280 hertz. Alright, so this frequency of the sound wave is gradually increased. Very easy question just for 1 mark. Determine the frequency of the wave when stationary wave is next formed. In simple words, they are asking when the next harmonic is formed. At what frequency the next harmonic is formed. So what harmonic was that? Matter of fact, we have written everything initially. That was the first harmonic. And if you have to find the next harmonic, you can use the formula for the second harmonic, for the frequency of the second harmonic. And what was that? We have it right in front of us. In that case, the second harmonic, F equals to V over L. So what we do is, for the second harmonic, F equals to V over L. Second harmonic, also known as first overtone, by the way, V was 340 divided by length of the tube was 0.60. If I hit it on the calculator, 340 divided by 0.60, 566, and in 2SF I can round it off to 570 degree hertz. And the other thing is the new frequency. In this one, the general formula is very simple. If you have to find the first harmonic, frequency of the first harmonic, just insert the value of n as 1. The second harmonic would be formed at 2 times of the first one. Since we rounded off the answer to 2SF, it was 283 something. And if you use the same answer, the actual one, and then you round off, you'll be getting 570, not 560. If you just carry forward the same one, then you get 560, and matter of fact 560 is also acceptable. But the actual value for this one was 283 something. And if you need to find the frequency of the next stationary wave, just multiply the fundamental frequency by 3. You get the third harmonic, which is also known as first overtone, or use the general formula for the frequency, which is for the third harmonic it was 3V over 2L, and the general formula was same, which is this one. For the first case, second case, this was the general formula, NV over 2L. Likewise, if you had to find frequency for the second harmonic, you use, instead of N, you write 2 V over 2L. 2 and 2 would be cancelled out. You'll be left with the same frequency equals to V over L, which is just the same thing that we have used over here.